SwayamPrabha. Digital India. Educated India.
Hello everyone. So in today's class we are going to start talking about random processes, and we are going to be considering a turbulent flow experiment where a component of velocity is actually measured. So we looked at PDFs. We started with probability, of course, CDFs, cumulative distribution function, probability distribution function. Then we went on to joint random variables, so naturally joint CDFs, joint PDFs. That took us to marginal CDFs, marginal PDFs, and then conditional PDFs. So now let's look at the actual process, some random process, and let's try to relate that to what we know about turbulent flows. So if U is a component of velocity in a repeatable turbulent flow experiment, and let's say it is measured at a particular location and time, it is completely characterized by its PDF, f of v. It's completely characterized by its PDF. However, let's say you consider the same velocity now as a function of time. So then a time-dependent random variable, we call it a random process. Right? An example would be, in the next slide, I've shown here a picture of velocity with time. And you will see that this velocity here is measured with time. And in fact, this is a sample path of the velocity measured with time at a particular point in space and a particular component, by the way, from 3 different repetitions. So there are 3 curves in the air from 3 different repetitions of a turbulent flow experiment. So it might be starting from almost the same value, but then it fluctuates. It looks chaotic, it looks irregular, isn't it? So it looks random to us. So this random process is characterized by, it could be like a one-time CDF and a one-time PDF, meaning at a single point in time, its variation is characterized by a one-time CDF. What do I mean by that? If I just take a single point in time, say t is equal to 4, at 3 different repetitions, I have 3 different values. That means at that particular point in time, I can represent the velocity, a single component of the velocity at a particular point in space, because of its random variation with different repetitions. I can represent it by a one-time CDF, by a one-time PDF. Why do I call it a one-time CDF or a one-time PDF? Because it represents the velocity at a single point in time. It represents the velocity at a single point in time. So that is what I mean. So that PDF, or in this case CDF, f of v comma t, is the probability of u of t at a specific point in time being less than v. And obviously the PDF can also be defined. So now the PDF is a function of time, right? F of v at t is del f del v, which is a function of, again, v and t. Now, I want to repeat this. This is a single component of velocity. It is measured at a single point in space, and we are considering one point in time. And we say that there is a distribution. It follows a random pattern. And as you know, this one-time CDF and PDF, it contains no joint information about U2 for 2 or more times. This does not have any information about what happens later or even before. So it contains no joint information about U of t at 2 or more times. So now that's the context I want to leave you with. Now let's consider 5 different random processes, radically different behavior, and that is illustrated in this particular figure here. 5 different random processes, and these are statistically stationary random processes. Statistically stationary means their statistics do not vary with time. The variables themselves could vary with time, as you can see. This is sample paths of 5 statistically random processes, statistically stationary random processes. And they have different characteristics. We'll go over that. So clearly the x-axis is time and the y-axis is whatever quantity that is measured, the random variable that is measured. That its variation with time is what is plotted for 5 different random processes. Now I'll come back to this. Each of these have the same one-time PDF. That means at a specific point in time, they have the same PDF. They have the same one-time PDF. But as you can see, they are so different from each other in spite of having a one-time PDF. So this goes to indicate that a one-time PDF cannot characterize by any means the variable completely. It does not give any joint information about 2 or more times, isn't it? That's what we are trying to say. So that means in order to completely characterize a random process, we need to know the joint PDF at all instants of time. So when you have a random variable being plotted here with time, this is a measurement, it's a velocity measurement, but it behaves randomly. So when you have this random variable that is plotted with time for different repetitions, in order to completely characterize it, you need to know that value, you need to know the joint PDF for all the times. So we are talking multiple times. That is why we are saying it is a joint PDF. And this, in this case, so we will have multiple distributions because you have multiple repetitions, and you will have a joint PDF because it has multiple times. All of this for a single component of velocity at a single point in space. You would have to do this for all 3 components and for all points in space for you to completely characterize the turbulent flow, isn't it? So imagine how complicated it's going to be. So if it is that complex, one way to simplify, one way to make our life easy is to consider the process to be statistically stationary. And many turbulent flows are statistically stationary, meaning after a certain period of time, the statistics are going to be constant. They are going to stay constant. They are going to not vary with time. So that's what we mean. A process is statistically stationary if all multi-time statistics are invariant under a shift in time. That is, for all positive time intervals and for all choices of t1, t2 to tn, we have f of the PDF of v1, t1 plus t, v2, t2 plus t, comma, so on and so forth. Vn, tn plus t is the same as f of v1, t1, v2, t2, so on, vn, tn. So what we are saying is with time it doesn't vary. So what is shown here in this particular figure, in this slide, is the instantaneous velocity. So obviously this will vary with time. We are talking only about statistics. So if I want to just show something here quickly, this is what a mean looks like for a turbulent flow. For example, so the mean is changing initially, but after a certain period it starts to remain constant. Same goes for the variance. So this is the mean and this is the variance. Let me use the same notation. So it is the variance. They are, as you can see, they are staying constant with time. Now let's go back to the 5 random processes that we had shown earlier. So here, like I was saying earlier, this is all characterized by the same one-time PDF. It still is showing very different behavior. So the one-time PDF is a standardized Gaussian, by the way. Just to be specific, all of them have a standardized one-time PDF. Now, the first one is a measured turbulent velocity. The second one is a measured turbulent velocity at a higher frequency than that of A. And it is clear, visually you can see, if you look at figure B, it fluctuates a lot more. So it is at a higher frequency. The third one is a Gaussian process with the same spectrum as that of A. So both of these have the same spectrum. The fourth one is an Ornstein-Uhlenberg process, which is a stochastic process. It's a random process with the same integral timescale as that of A. So this one has the same integral timescale. Let's call that tau. Has the same spectrum. Let's call that E. And the fifth one is the jump process, again a stochastic process with the same spectrum as that of D. So these two have the same spectrum, E. Alright, so these are the 5 random processes. Now the first point I want you to take away from here is they have the same one-time PDF and it happens to be a standardized Gaussian. And in spite of that, they are showing radically different behavior. So what does this all mean, right? Now let's first define what a statistically stationary random process is. So a turbulent flow after an initial transient period can reach a statistically stationary state, let's call that SS, even though the flow variables u of t vary with time, the statistics don't, they stay constant. Now for a statistically stationary process, the simplest multi-point statistics that we can consider is the autocovariance. So let's call that RFS, which is defined as u of t times u of t plus s and the average of that. So it is clear what we are trying to do here. The autocovariance is the correlation of velocity of a signal, right? Velocity at a point with the velocity at that same point, same component. Velocity at the same point but at different point in time. It is the correlation of those two values. S is the time lag between them. So that is the autocovariance. It is the correlation between the same velocity component at the same point in space but at a different point in time. So that would be the autocovariance, and S here is the time lag. Now you want to, just like earlier we had covariance, now we have autocovariance, so we would have an autocorrelation function like a normalized value of the autocovariance, which is basically the autocovariance divided by the variances, isn't it? By the variance. So you have ut times ut plus s divided by ut squared, average of that, where ut is the fluctuation. Now since it is an SS, it is a statistically stationary process, the mean, variance, the autocovariance and the autocorrelation function, they do not depend on time, they are a constant. So the autocorrelation function is a correlation coefficient between process at times t and t plus s. So just like you had correlation coefficient earlier, now you have an autocorrelation function which is at 0 is going to be 1. It is going to be a number that is between -1 and 1. That is what this means. And it is going to be an even function. So what does that mean? So rho of s is equal to rho of minus s. What we are trying to say is whether it is a time lag or a time lead, it doesn't matter. It is going to be the same value. So it's an even function. It doesn't, because you are taking a product of two values, right? One is lagging behind the other, one is leading over the other. So whether s is positive or negative, it doesn't matter, it will have the same value. Now, if ut is periodic, u of t plus t is equal to ut, then the autocorrelation function is also periodic. So rho of s plus t is rho s. So if you have a sinusoidal wave, then the autocorrelation function is also going to be periodic. Hope that is clear. So now let's define the integral timescale, because all of this was required in the 5 random processes that we described earlier. So the integral timescale is defined as the integral of rho s ds. Okay? This comes from the fact that if you take a turbulent flow, the correlation will diminish as the lag time increases. Physically, what does that mean? If I try to correlate between values of velocity at one point in time to values of velocity that are much further in time, much in the future, very much in the future, then as my lag time increases, my correlation is reducing. Eventually, there will be no correlation between velocity at one point in time to velocity that is much further out in time. So the correlation is going to keep decreasing, which means the integral of the autocorrelation function is going to converge. You are going to get a finite value because the correlation function is decreasing. It is decreasing and it is eventually going to 0. So you're going to have the integral timescale 0 to infinity, the integral timescale defined as 0 to infinity, the autocorrelation function rho of s ds. And this figure I have described earlier, it basically is indicating that how for a statistically stationary process, the statistics don't vary with time after a certain point in time. So this is the transient period. And this is the statistically stationary period. So now let's think about the 5 random processes that we had described earlier, isn't it? So let's think about what the autocorrelation means. Now the higher frequency process, so I'll have to go back and forth here. The higher frequency process B has a narrower autocorrelation function than the lower frequency process A. First of all, keep in mind that this has a higher frequency. B, let's call it FB, right? FB has a higher frequency than FA. It's clear. I was saying earlier that even on observing figure B, you will see that there are more fluctuations in B, indicating that it has higher frequency components. So B has a higher frequency than A, which means it is going to have a narrower autocorrelation function. Physically, what does that mean? So if you think about the autocorrelation function, it's like the normalized version of the autocovariance, right? So if you have a higher frequency, things are happening at a much smaller time scale. So the further S is, the less correlated it is going to be. The further the lag time is, it correlates with events that are much closer to itself in time because it has a smaller time scale. So it correlates less with events that are further in time compared to a lower frequency case. So that is what we mean by higher frequency process has a narrower autocorrelation function than does the lower frequency process A. So that is what is plotted here. This is A and this is B. You can see that it has a much narrower autocorrelation function compared to B. So they have the same one-time PDF, but the autocorrelation function is different. So we are trying to see how different statistics are different even though their one-time PDF is the same. Autocorrelation is one of them. You can see that for B it is narrower. What else? Processes D and E both have an autocorrelation function defined by this with the same integral time scale as that of process A. So D and E have the same integral timescale as process A. So apart from B, all processes have the same integral timescale. So coming here, you will see that D and E, they have the same integral timescale as A and C. I'm sorry. D and E have the same integral timescale as A and C. This is A and C. They have the same integral time scale. The only one that is different is B. So A, C, D and E have the same integral time scale. They have different autocorrelation functions, but they have the same integral time scale. Integral time scale is obtained by integrating the entire autocorrelation function. The only one that has a different autocorrelation function is B, or a different time scale is B. So that is this one here, which has a narrower autocorrelation function. So that's what we've been trying to get at in terms of looking at the autocorrelation function for the different random processes. So as much as these processes have the same one-time PDF, they look different, that is for sure, and it looked like only B had a different integral time scale. A, C, D and E have the same integral time scale. You wouldn't guess that by looking at this figure. So there are a lot, what we are trying to say is there are a lot more parameters that you need in order to completely characterize a system. And just by taking a one-time PDF is not enough. The autocovariance is a start. That is one of the variables that you can take. But this is all possible also because these are statistically stationary processes, meaning they are not changing with time. The statistics are not changing with time. So we are able to consider a covariance, RFS, which is not changing with time. Now, that takes us to what is called the frequency spectrum. The autocovariance and the frequency spectrum are Fourier transform pairs. Meaning, the frequency, what we define as this frequency spectrum is basically the Fourier transform of the autocovariance. So the autocovariance RFS is UT times UT of S, which is in terms of the autocorrelation function, it is UT squared times rho of S, right? This is the variance. So UT squared mean times rho of S. Now this autocovariance is the inverse Fourier transform of the frequency spectrum, or the frequency spectrum is the Fourier transform of the autocovariance. So E of omega is, this is how you define a Fourier transform, 1 over pi minus infinity to infinity RFS e to the minus I omega s ds. Now you know that since RFS is an even function, we saw earlier that rho of s is an even function. Remember, whether s is a time lag or a time lead, the value remains the same, isn't it? Because as long as you're just taking the product of two variables in time. So it doesn't matter whether one is behind the other or the other one is ahead of the other, the value is the same. So in that sense, RFS is an even function. You have an even function multiplied by e to the minus I omega s. Remember, e to the minus I omega s is cos omega s plus I sin omega s, where I is the complex number. And cosine omega s is an even function, whereas sin omega s is an odd function. So when you have an integral going from minus infinity to infinity and taking an odd function multiplied by an even function, that is going to cancel out to 0. You're only going to be left with even functions. That is what you end up with here. Except you will now have a 2 over pi, because of minus infinity to infinity, it takes 2 times the 0 to infinity integral. So you have the 2 over pi 0 to infinity RFS cosine omega s. That is because the cosine function is an even function and RFS is an even function as well. An odd function multiplied by an even function cancels out to 0 if you are taking over a symmetric range like minus infinity to infinity. Hope that is clear. So this is how the frequency spectrum is defined. E of omega is 2 over pi 0 to infinity RFS cosine omega s. Similarly, the inverse Fourier transform would be defined as the autocovariance is half minus infinity to infinity e of omega e to the I omega s ds. So this is the inverse Fourier transform. This is Fourier transform and this is the inverse Fourier transform. I'm just going to call it IFT. So again, using the same substituting e to the minus I omega s as cosine omega s plus I sine omega s, this would be 0 to infinity e of omega cosine omega s ds. Again, because you are removing the odd function out. So essentially, RFS and E of omega, they contain the same information. It's basically the autocovariance itself in frequency space. RFS is real and even, so is E of omega. That's also real and even. Remember, now what we are doing is we are going from physical space where we represent things in time, take correlations in time, and we are taking a Fourier transform and representing the frequency spectrum in frequency space. So this velocity fluctuation has a spectral representation as the weighted sum of Fourier modes. That is what we are doing when we are taking it as when we are taking a Fourier transform. We are saying that the velocity is now represented by sum of a lot of Fourier modes. This is a way to analyze the frequencies associated with a turbulent flow. So in today's class, what we have done is we started by looking at random processes, and we, as an example, we looked at 5 different random processes. We looked at what a statistically stationary random process is. In those 5 random processes, all of them had the same one-time PDF, but they had, and their other statistics were vastly different from each other, indicating the fact that to completely characterize a system, you need more than just a PDF. You need more than just a one-time PDF. That took us to the definition of the autocovariance, the autocorrelation function, and finally to the frequency spectrum. We are going to take this forward and look at the frequency spectrum and the spectrum tensor in the next class. Thank you.